This is the video presentation for the example problems of Chapter 12, Torsion in Circular Sections. First of all, example 12.1, calculate the internal torque at sections RR and SS in the shaft shown. Okay, so what we have here is we have a shaft that's used for power transmission. The power is coming in on this driver pulley, and it's coming in with 2,400 inch-pounds of torque. And then we have three other pulleys that are actually removing power from this system. Okay, the pulley at A is removing 600 inch-pounds. The pulley at C is removing 1,000 inch-pounds. That could be a gear drive or a belt drive or something like that. And then 800 inch-pounds are removed. So essentially what happens here is this shaft is in equilibrium even though it's transmitting power, rotating at some angular velocity. Okay, solution. Note that pulley B is the driver pulley. The other pulleys are takeoff pulleys. The torques of 25 pound-inches at B is balanced by the three torques of 600, 1,000, and 800 pound-inches at C, A, C, and D respectively, which are going in the opposite direction. Therefore, the entire system is in equilibrium, at a steady state equilibrium. That is, neither gaining nor losing speed. If the system is in equilibrium, then every segment of the system must also be in equilibrium. So, to solve for the torque at any of these points along the shaft, here's the way I like to do it. I like to draw a torque distribution diagram. So the equilibrium can be represented by a torque distribution diagram to find the torque state at any point. So I'm using torque being applied as being positive and torque being removed as being negative. Okay, the bearing locations do not add or subtract any torque. I mean, there's a little friction there, but we're neglecting friction for this particular problem. Okay, so from the bearing to point A, we have a torque status of 0. At point A, we're subtracting 600 pound-inches from the power in the shaft, so that's negative 600. And then at point B, we're adding 2,400 pound-inches, so that takes us from negative 600 up. This is kind of like a shear and bending moment diagram. A shear diagram that we're going to be talking about in the next lesson. So therefore, at section RR, we're talking about 600 pound-inches being the torque at that section, and then at section SS, we're talking about 1,800 pound-inches at section SS. So using the sign convention as adding torque is positive, subtracting torque is negative, the bearing locations do not add nor subtract torque. The torque at section RR is 600 pound-inches, and the torque at section SS is 1,800 pound-inches. Next one, example 12.2. Calculate the allowable torque that can be applied to a circular shaft. The allowable shear stress is 83 MPAs. First of all, assume that the shaft is solid and has a 150 millimeter diameter. And then B, solve it again, assuming that the shaft is hollow and has an inside diameter of 150 millimeters and an outside diameter of 150 and inside of 125. So solution A, the solid shaft. Find the polar moment of inertia formulas inside your textbook. That's J equals pi d4, d to the fourth divided by 32, and then solve that in terms of millimeters. And then calculate the allowable torque. That's equation 12.3. The allowable torque is the allowable stress, shear stress, times J divided by C, which is the distance to the outside of the shaft. Next, we're going to do it for the hollow shaft. So the allowable torque is going to be based on this formula here. Again, the same formula, except the difference is we're going to be using a different formula for calculating J. So J is the outside diameter to the fourth minus the inside diameter of fourth divided by 32 times pi. Okay, next example. Calculate the maximum shear stress developed in a circular steel shaft when subjected to a torque of 95,000 pound-inches, assuming that the shaft is solid with a 4-inch diameter. Okay, so first step, we're going to find the polar moment of inertia. That's pi d to the 4th divided by 32. Next, we're going to calculate what the shear stress is, and then note that the maximum shear stress is developed at the outer surface of the shaft. Therefore, our C that we're going to substitute in this equation is 2 inches. Now again, we talked about this in the presentation. For design problems, we need to find a shaft size based on a certain parameter, either the allowable torque or the allowable twist, and then we're going to calculate that, but our actual answer is going to be in a next available shaft size. So we need to consult table 12.1 to find the next available shaft size. Okay, example 12.4. Calculate the required diameter of a solid circular shaft that must resist a torque of 20 kilonewton meters. The allowable shear stress in the shaft is 83 megapascals. Select a shaft diameter to use. Okay, so I wrote this in the proper format of setup for our homework solutions. So given a solid circular steel shaft must resist a torque of 20 kilonewton meters with an allowable stress of 83 MPa, find the proper shaft diameter. Okay, so when we're working in SI units, the first thing we're going to do is put all of our terms in units of newtons and meters. Okay, so we're going to put our torque in terms of Newton meters. That's 20 times 10 to the 3rd Newton meters. And then the allowable stress is in MPAs, and then MPAs are Newton meters. So that's 83 times 10 to the 6th Newton meters squared. Next, we're going to use equation 12.4 to solve for the diameter. So that's the cube root of 16t divided by pi divided by the allowable torque. And what we get is 0.107 meters when we solve that equation, or 107 millimeters. So then we're going to go to table 12.1 and then use a shaft to the nearest 5 millimeter increment. So therefore our answer is going to be use a 110 millimeter shaft. We're going to pick this up on the next movie.